Think about the motion that defines our reality. Everything around us is constantly vibrating, driven by energy and heat. But what happens when you systematically strip that energy away? You descend past the freezing point of water, past the cold of deep space, until you approach a theoretical limit. This is absolute zero, or minus 459.67 degrees Fahrenheit. Here, the chaotic movement of atoms slows to a near-perfect standstill, revealing a strange and quiet state of matter where the usual laws of physics begin to blur. It is a place of ultimate order. If this type of clear, scientific exploration interests you, a gentle like and subscribe is always appreciated. Let's look closer at this point where nature's motion finally comes to rest. To understand the deep silence of the universe, we must first change the way we perceive the familiar world immediately around us. Absolute zero is not merely a cold temperature. It is a fundamental concept, an idea that redefines our relationship with reality. It begins with a shift in perspective regarding simple, everyday sensations. When you wrap your hands around a warm mug of tea on a rainy morning, or when you step outside and feel the sharp bite of winter air on your skin, you are not actually sensing a physical substance. Heat is not a fluid that pours from one object to another, and cold is not a physical blanket that covers the world. What you are feeling, in the truest scientific sense, is motion. At the most microscopic level, the universe is never truly still. Every object you touch, every breath of air you take, and even the cells within your own body are composed of atoms and molecules that are in a state of constant, restless agitation. They vibrate, they jiggle, and they bounce off one another in a chaotic dance that never ends. This invisible kinetic energy is what we register as temperature. When you touch something hot, you are feeling atoms striking your skin at high speeds, transferring their energy to you. When you touch something cold, the opposite happens. The slow-moving atoms of the object absorb energy from your faster-moving skin. Therefore, the difference between a blazing fire and a block of ice is simply the speed of this atomic dance. Now, imagine an experiment where we have a dial that controls this motion. If we turn the dial down, the atoms begin to move more sluggishly. As they slow down, the object becomes colder. If we continue to turn the dial, extracting more and more energy, the vibrations become fainter. The chaotic bouncing settles into a quiet shudder. Logic dictates that if we keep turning this dial, eventually we must reach a limit. There must be a point where the motion simply ceases entirely. You cannot go slower than a dead stop. This theoretical stopping point, where all thermal motion grinds to a halt, is what scientists call absolute zero. In the language of measurement, this point sits at exactly negative 273.15 degrees Celsius, or negative 459.67 degrees Fahrenheit. These numbers are so extreme that they detach themselves from our human experience. They are far lower than the coldest winter ever recorded in Antarctica, and colder even than the empty voids between the stars in deep space. This is not just a temperature that requires a heavy coat. It is a temperature where the fundamental scaffolding of matter begins to lock into place. It represents a state of ultimate order, a stillness so profound that it feels less like a weather condition and more like a rigid mathematical argument with nature itself. However, the universe has a way of protecting its limits. Absolute zero is often described as a destination, but in practice, it functions more like a horizon. No matter how fast you move toward the horizon, it remains in the distance. Similarly, absolute zero is physically unreachable. This is due to the fundamental laws of thermodynamics, specifically the third law, which acts as a cosmic gatekeeper. As scientists try to cool an object down to this ultimate limit, the effort required to remove the remaining heat increases exponentially. The universe seems to pull the goal away, keeping a tiny fraction of energy always just out of reach, like a mirage shimmering on a desert road. We can get incredibly close, within billionths of a degree, but the perfect zero remains a theoretical purity that reality will not allow us to touch. Yet, in our attempts to reach this forbidden temperature, we have discovered that the approach itself transforms matter in ways that defy logic. As we strip away the energy of motion, the familiar rules of classical physics, the rules that govern bouncing balls and falling apples, begin to dissolve. In their place, the strange and ghostly laws of quantum mechanics take over. At these ultra-cold temperatures, atoms lose their distinct identities. In our warm, everyday world, an atom is like a singular individual, bouncing around independently. But near absolute zero, they start to behave more like waves on a pond. As these waves expand and overlap, the atoms begin to merge. They synchronize their behavior, collapsing into a single, unified entity known as a Bose-Einstein condensate. This is a state of matter that was once only a mathematical prediction on paper. In this state, you can no longer tell one atom from another. They move together, react together, and exist together as if they were one giant superatom. It is a ghostly transformation where the boundary between individual particles disappears, leaving behind something that flows without friction and exists in a state of perfect cooperation. It is not just frozen matter. It is a new way of existing, revealing that at the bottom of the temperature scale, the universe operates on a completely different operating system. This shift in behavior forces us to confront the nature of reality itself. The quantum rules that govern absolute zero do not care about our common sense or our perception of cause and effect. This temperature, at the very bottom of possibility, acts as a doorway to the hidden machinery of the cosmos. But to truly appreciate how strange this is, we should pause and consider why we even have a temperature scale that ends at zero. Why is there a bottom at all? To understand this, we have to look back to a time before digital thermometers and precise scientific laws. For most of human history, heat was a mystery. It was simply a sensation felt in the bones. Fire provided comfort, and ice caused pain. There was no understanding that these feelings were connected to invisible particles. It wasn't until the 19th century that scientists began to realize that heat was quantifiable. Lord Kelvin, a physicist whose name is now immortalized by the scientific temperature scale, proposed that if heat is just motion, then zero shouldn't be the freezing point of water that is just an arbitrary milestone meaningful only to humans. True, zero should be the point where there is zero motion. This realization created the Kelvin scale, which starts at absolute zero and counts up. On this scale, there are no negative numbers. It established a solid floor for the universe. This boundary, absolute zero, is the closest physics can get to true silence. In this silence, the randomness that defines our universe calms down. Entropy, which is a measure of disorder, drops to its minimum. It is unsettling to think about because our understanding of time is deeply connected to change and motion. We measure time by watching things change, a clock ticking, a planet rotating, a heart beating. At absolute zero, where motion is theoretically suspended, the concept of time begins to feel slippery. If nothing changes, Does time still pass in the same way? Despite this eerie stillness, the frozen world is not empty. It is in this domain of near-zero energy that nature hides some of its most exotic secrets. Scientists have observed superfluids, liquids that can flow forever without any friction. If you stirred a cup of superfluid tea, it would continue to swirl for eternity, never slowing down, because the atoms have ceased to collide in the way we understand. We see superconductors, materials that carry electricity with zero resistance, allowing energy to flow perfectly without wasting a single spark as heat. These are not just magic tricks performed in a laboratory. They are glimpses into the fundamental fabric of matter when the noise of heat is silenced. It is easy to think of these experiments as distant and abstract, disconnected from our daily lives. However, the pursuit of the cold has already reshaped the modern world. The technology inside your smartphone, the microchips that power the internet, and the lasers that carry data across oceans all rely on an understanding of quantum behavior that was first studied in the deep cold. The precision of atomic clocks, which synchronize the GPS satellites orbiting Earth, allows you to find your way home with meter-level accuracy. These clocks work by measuring the vibration of atoms, a measurement that becomes incredibly precise only when we understand how to control and cool those atoms. Even our most futuristic ambitions, from powerful quantum computers that could solve the unsolvable, to theories about the Big Bang and the eventual heat death of the universe, are informed by what happens at these lower limits. The closer we look at absolute zero, the more it acts like a mirror. It reflects the limits of our understanding. It challenges our definitions of energy and matter. We are not just studying cold. We are studying the baseline of reality. So, let us continue to drift downward in our imagination, dropping 1 degree at a time. We must remember that the world at absolute zero is not a barren wasteland. It is a place of quiet revelations, waiting in the deep stillness where the ordinary rules loosen their grip and something new begins to emerge. If absolute zero is the bottom of the scale, then this is the part of the story where the scale itself starts to feel unreal. The very phrase absolute zero sounds definitive, almost like a challenge or a dare invented by physicists. It represents a number so extreme that it hovers at the edge of meaning. -273.15 degrees Celsius, not a fraction warmer, not even the faintest flicker of heat left in it. It stands as the strange, unreachable border where temperature ceases to be a thing we can fully imagine. For the vast majority of our lives, temperature is a simple, manageable concept. We live in a narrow band of existence, filled with warm blankets, cool breezes, hot coffee, and cold hands on winter mornings. We understand numbers like 40 degrees Celsius as sweltering, or 0 degrees Celsius as icy. We tend to think we have seen the whole scale of what nature offers. But the truth is that our everyday experience barely skims the surface of what temperature actually means. Because, as we have established, temperature is not a sensation, it is motion. It is the metric of how much the tiny building blocks of matter are jostling against each other like an endless, invisible crowd. When things get hotter, those particles bounce harder, collide faster, and spin with more aggressive energy. And when they get colder, they simply slow down. But here is where the concept turns strange. In the upward direction, things can get hotter and hotter the center of the sun, the blast of a supernova, but the slowing down process has a hard floor. There is no infinite descent. There is a final rung on the ladder. Yet, reaching that rung is a task that fights against the universe itself. Each step downward costs significantly more energy to take than the one before it. It becomes a battle of diminishing returns until you reach a place where removing even a fraction of a degree is a monumental scientific effort. This brings us back to the origin of the concept. The idea of absolute zero emerged from the slow, steady march of science centuries ago. It solidified when we began to understand that heat wasn't a magical substance to be poured, but a mechanical property. People like Lord Kelvin realized that if heat is motion, there must be a point where motion ends. And if motion ends, then temperature must end too. That number became zero on the Kelvin scale, not just as a matter of convenience for calculations, but as a boundary drawn by nature itself. But here's the part that feels almost mischievous on the part of the universe. While this number has a specific name and a neat place in our textbooks, reality refuses to let us actually arrive there. No matter how clever our engineering becomes, no matter how many lasers or magnetic traps we build to slow atoms down, we will never truly touch absolute zero. The laws of physics stand in the way like an unmovable signpost. The closer you get, the harder it becomes to cool anything further. The last scraps of motion cling stubbornly to matter like whispers you can't quite quiet completely. And yet, even though we cannot reach it, that has not stopped scientists from chasing it, piece by piece, degree by degree. And every time we push a little closer, the world beneath those temperatures becomes stranger. What was once solid and ordinary begins to behave in ways that look like they belong in science fiction. Gases collapse into that single unified state where every particle shares the same quantum identity. Metals lose all electrical resistance and become perfect conductors. Fluids learn how to flow forever without slowing down, as if friction simply gave up and walked away. This is not just a laboratory curiosity. The fact that absolute zero exists as a concept changes the way we see the universe itself. It tells us there is a floor beneath all the restless energy we live with, a kind of cosmic silence that everything leans toward but never quite reaches. And it raises a question that is far more unsettling than it first appears. If the universe has a temperature it can never reach, what does that say about its limits? If we could reach it, would time itself mean anything? Because if you think about it deeply, temperature is tied to time in a way we do not often notice. The hotter something is, the more its particles move, the more collisions there are, and the more events happen per second. Now, imagine dragging everything down to absolute zero, where motion halts entirely and collisions stop. What would time look like then? Would it still make sense to talk about seconds passing if nothing is changing in those seconds? These are not just thought experiments for the late hours of the night. Scientists have built machines to creep down to billionths of a degree above that unreachable zero. They do this not because they expect to beat the laws of nature, but because they want to see what happens when the familiar scaffolding of our world falls away. Every single rule we take for granted has to be rewritten in the language of quantum mechanics. In those labs, they have seen things that look like the universe itself turning inside out. But even as we chase that number, even as we come closer to the edge of this impossible temperature, absolute zero remains more like an idea than a destination. It is the ultimate boundary, the place that gives shape to the scale above it. Without it, our concept of temperature would not have an anchor. It is not just a cold point. It is the reference that every degree of warmth is measured against. And that means that in a strange way, this temperature that shouldn't exist is the one that holds all the others in place. And so, we continue our journey downward, drifting past the freezing points we understand into a realm where the map begins to fade. We follow this temperature scale step by step, chasing a horizon that, by its very nature, never stops retreating. Every new experiment conducted in the quiet corners of advanced laboratories brings us a fraction of a degree closer, yet we never quite arrive close enough to erase that final gap. And it is precisely within this gap, this infinitesimally small sliver of existence between almost zero and absolute zero, that the universe hides its most profound secrets. If absolute zero were simply another destination, a static point on a list that we could reach, verify, and move on from, it would lose the mystique that has driven physicists for over a century. It would just be a number. But because it stays out there, permanently untouchable, it sets the stage for a transformation that is nothing short of magical. As we descend, the environment around us does not just get colder, it gets fundamentally stranger. The road toward absolute zero is not a smooth highway. It is a path marked by distinct stops where the ordinary world fades away and the rules of reality shift into something unrecognizable. The closer we get, the more the world begins to feel unfamiliar. This is not simply because the numbers on the digital thermometers are dropping into ranges that look like errors. It is because every step downward acts like peeling back a layer of reality that we never knew existed. In our daily lives, temperature is tangible. It is the warmth of the sun or the chill of snow. But down here, temperature stops feeling like a sensation you can touch. It starts feeling like an abstract idea, a countdown into a void where all the busy, restless, kinetic energy we take for granted slowly surrenders to silence. Consider for a moment what happens when you cool an object in the ordinary world. You can see the physical effects with your own eyes. Gases condense into liquids. Liquids thicken and freeze into solids. Metals contract, becoming rigid and brittle, ready to snap under pressure. The air itself feels heavier, denser. But underneath these visible changes, the real drama is happening at a scale too small to see. Motion is losing its strength. Every atom, every molecule that constructs the chair you sit on or the air you breathe is slowing down. They are not stopping yet, but they are edging closer to a kind of stillness that the human mind struggles to comprehend. We struggle with this because true stillness is not something we have ever actually experienced. The room you are in right now, no matter how quiet, is a riot of motion. The air surrounding you is a chaotic storm of nitrogen and oxygen molecules, moving at hundreds of miles per hour, colliding billions of times every second. Your own body is a biological factory of chemical reactions, buzzing with thermal energy. Everything you know is vibrating with the restless hum of heat. But as you count down toward absolute zero, that hum begins to fade. It is not a sudden silence. It is a gradual surrender, occurring one tiny fraction of a degree at a time. And with each step of this surrender, the rules of the game begin to bend. In the warm world, atoms act like little individual marbles, hard, distinct, and bouncing off one another. But as the cold deepens, they stop behaving like separate objects. They begin to blend. The boundaries of here and there start to smudge. The closer you get to zero, the less they act like isolated particles, and the more they move together, as if the entire world is slipping into a single, collective rhythm. This description is not merely a poetic metaphor. In the deep, crushing cold of this descent, particles genuinely begin to lose their individuality. Their quantum states, the mathematical descriptions of their existence, expand and overlap until they become indistinguishable from one another. This phenomenon is why scientists often describe the process of extreme cooling not just as lowering temperature, but as watching matter collapse into unity. It is a profound shift in identity. Furthermore, It is not just the atoms that change, it is the very logic we use to measure them. At room temperature, or even in the coldest depths of an Arctic winter, our understanding of heat belongs to the classical world. This is the world of thermometers, of steam engines, of simple cause and effect, where energy flows smoothly like water. But near absolute zero, that classical thinking shatters. The ordinary mathematics of thermodynamics stops working. What replaces it is a view of the universe that has been hiding in plain sight all along, the quantum world. Down here, even the definition of temperature begins to blur. We know temperature depends on motion, and motion depends on energy. In our daily experience, energy feels continuous. You can turn a dimmer switch smoothly from bright to dark, but in the quantum realm, energy is not smooth. It comes in discrete packets, or quanta. Imagine walking down a staircase that is crumbling away into darkness. In the warm world, the slope is like a ramp. You can stand anywhere, but as you get colder, the ramp turns into stairs. Each step takes you lower, but the steps are rigid. You cannot stand between them. You are either on one energy level or the next. These are quantized states. This structure creates strange, sudden drops separated by spaces where nothing seems to happen, until suddenly a transition occurs. This fundamental staircase structure of reality explains why the final approach to absolute zero is so incredibly difficult. Cooling an object from 10 degrees to 1 degree feels relatively easy. It's just moving down the ramp. But cooling it from 1 degree to 1,000th of a degree, and then to a billionth, is like dragging the universe uphill with your bare hands. Every bit of energy you try to remove gets harder to pull away because there is less of it left to grab. Each scrap of heat is locked tighter than the last. As you descend these final quantum steps, the price of cooling goes up. Every step down costs exponentially more work and energy. It is as if nature built a hidden resistance into the bottom of the scale, a quiet defense mechanism designed to prevent us from ever reaching that final, perfect zero. But this resistance is also what makes the descent so fascinating. The closer you get, the stranger the scenery becomes. You start to witness phenomena that simply do not exist anywhere else in the cosmos, not in the heart of stars, not on the frozen surface of Pluto, not in anything we would call ordinary matter. This is the realm where superfluid helium defies common sense, climbing up the walls of its glass container and spilling over the side as if gravity has ceased to matter to it. This is where atoms that should be bouncing around like a room full of unruly children suddenly settle down and march in perfect lockstep, as if an invisible conductor has raised a baton to silence the noise. This is where electrons, which usually scatter and bump into atoms, creating resistance and heat, suddenly pair up and flow without any resistance at all, moving in a loop that could theoretically last forever without fading. Every one of these phenomena acts as a reminder that we are no longer dealing with just a number on a scale. This is not just cold. This is what happens when you strip the universe down to its barest, most naked state. When you peel away the layers of thermal noise, you are left with the fundamental rules that have been buried underneath everything else since the Big Bang. And here lies the strangest paradox of all. The closer you move toward that ultimate nothingness, the more you realize it is not empty. It is not a void. It is full of hidden order. It is rich with physical laws that only reveal themselves when the chaos of heat is removed. Absolute zero sounds like an ending, a death of motion, but in the lab, it behaves like a beginning. It is a clean slate where new forms of matter are born. This realization is what keeps scientists chasing the unreachable. Every step down is not just about achieving a colder temperature record. It is about peeling away one more layer of normal to discover what reality looks like at its foundation. If we keep counting down past the millikelvins and into the microkelvins, we find even more waiting for us. We reach the point where motion does not just slow, it practically vanishes from our perception, and matter starts to act in ways that seem impossible. This is where heat stops being a sensation and turns into something you can almost watch unravel. When you reach the very edge of the thermometer and push further toward absolute zero, the behavior of atoms shifts entirely. At the temperatures you and I know, atoms are hyperactive. They vibrate, jostle, and crash against each other in a quiet, endless chaos. That constant dance is what keeps our world fluid and dynamic. But as you push toward the limit, the dance slows down so drastically that the time between one movement and the next stretches out. The jostling disappears. In this frozen world, an atom sinks toward its lowest possible energy state, the ground state. There is nowhere left for it to go. And at that moment, the rules flip. It is not just that the atom is still. It is that stillness itself becomes a new kind of motion, defined not by classical physics, but by quantum mechanics. At these unimaginably low temperatures, atoms stop acting like tiny billiard balls entirely. They start acting like waves. These are waves of probability, spreading out in space. As they spread, they overlap with the waves of their neighbors. This overlapping gives rise to the Bose-Einstein condensate, a state of matter so alien it barely seems real. In this state, thousands or millions of atoms lose their separate identities and merge into one unified entity. Imagine a crowd of people walking down a street where suddenly everyone stops making individual choices and begins to move in flawless unison, as if they are all part of a single body. Each step, each shift is perfectly aligned. That is what matter does near absolute zero. Individuality is erased. The entire system behaves like a single, enormous superparticle. It is a glimpse of reality with the noise turned off. But even here, the stillness is not absolute. There is a catch. Deep in the heart of quantum mechanics lies a concept called zero-point energy. This principle dictates that you can never remove all the energy from a particle. Even at absolute zero, atoms retain a faint, ghostly shimmer of motion. They have a tiny, irreducible vibration that refuses to vanish. It is as if the universe has written a fundamental law that says, nothing can ever be perfectly still, not entirely, not even for a moment. This residual vibration is what saves absolute zero from being a reachable destination. It ensures it remains a horizon. It is a boundary defined as much by what you cannot do as by what you can. This uncrossable line is why scientists continue to build colder and colder machines, dilution, refrigerators, and magnetic traps to push deeper into the decimal points. They do not expect to reach zero. They go there because every step closer reveals what matter is hiding in this strange borderland between motion and stillness. And what they find changes everything. We mentioned superfluids earlier, those strange liquids that lose all viscosity. When cooled almost to zero, they flow without friction. If you stirred a cup of superfluid coffee, it would continue spinning for millions of years. It creeps up walls not because it is alive, but because the friction that usually holds liquids back has simply stopped existing. We see superconductors, where electrical resistance vanishes, allowing current to flow perfectly. These are the rewards of the descent, the treasures hidden in the deep cold, waiting for us to quiet the universe enough to see them. And so, electrons begin to flow forever in a seamless loop, circulating without losing a single scrap of energy. It is as if the concept of waste itself, the idea that every action must have a cost in heat, has been erased from the rulebook. These phenomena sound impossible, like magic tricks or violations of nature, but they happen right here in our physical world. They occur only because we have learned how to walk atoms almost to the brink of total stillness, and then simply watch what they do. The closer we look, the clearer it becomes that absolute zero is not really an endpoint or a finish line. It is a threshold. It is a place where a different version of reality waits quietly, just out of reach, acting like a shadow world beneath the one we know. And within that frozen quiet, even the concept of time begins to feel different. We measure time by change at tick of a clock, the vibration of a quartz crystal, the orbit of a planet. But if motion slows this much, if atomic collisions nearly stop, and atoms merge into a single shared existence, what does it even mean to talk about 1 second passing after another? How do you measure the flow of time when almost nothing is changing to mark its passage? It is a question that physicists do not answer so much as circle around, because every time we look closer, another layer of this strange, quiet world peels away to reveal something new. And if this is what happens when motion freezes, then what happens next might be even stranger, because at these temperatures, it is not just the atoms that begin to change their behavior. It is the very fabric of what we think energy is. The deeper we go, the more it starts to feel like we are not just studying cold anymore. We are studying the foundations of everything. The deeper we descend into the Kelvin scale, the closer we come to the point where heat itself loses every foothold it has. We are entering a domain where warmth is not just rare, it is physically impossible. It is a place where energy, this restless, invisible currency that drives storms, engines, and biological life, runs out of moves to make. It is a game of chess where all the pieces have been captured, leaving nothing but the board. To understand why this happens, we need to remember what heat really is, stripped of our human perceptions. For most of us, heat feels like a simple sensation. You touch a fresh mug of coffee and your nerves say, hot. You step outside on a bitter winter night and your skin says cold. But beneath those biological signals, heat is nothing more than motion. It is kinetic energy. It is atoms jiggling, vibrating, and colliding against one another in a constant, chaotic shuffle. Every bump and every tiny exchange of momentum creates the phenomenon we call temperature. But as we keep pushing down the scale, stripping away the energy from that motion, we begin to reach a strange frontier. Every degree we remove takes us closer to the ground state, the point where there is no extra motion left to drain. The particles do not just slow down, they collapse into their lowest possible state of energy, a basement level beneath which they cannot sink. And at that exact point, heat, the very thing we have been meticulously cooling away, simply ceases to exist. It is here that the third law of thermodynamics steps in like an unbreakable barrier, a cosmic stop sign. This law states that as you approach absolute zero, the amount of energy and work required to remove those last remaining scraps of entropy grows infinitely large. In other words, nature does not let you hit zero. The cost of extracting that final flicker of movement becomes infinite. It is not a matter of building better technology, more powerful lasers, or bigger magnets. It is a fundamental rule of the universe's architecture. But even though we cannot physically touch that 0 point, every step closer reveals something astonishing. Because when energy drains out of a system and the chaotic motion fades, what is left is not emptiness, it is order. The wild randomness of particles crashing into one another starts to settle. In the warm world, atoms are like a panicked crowd, running in all directions. In the cold world, they become a disciplined army. In that deep quiet, new behaviors emerge, behaviors that can only exist when the usual chaos has been frozen away. One of the most striking examples of this newfound order is found in those exotic states of matter we touched on, superfluids and Bose-Einstein condensates. These are not just scientific curiosities to be written about in journals. They are physical demonstrations of what happens when heat loses its grip entirely. When energy has been drained so thoroughly that the thermal noise is silenced, the only thing left guiding matter is the subtle, precise machinery of quantum physics. In this place, friction disappears, because friction is just the conversion of motion into heat. If you cannot create heat, you cannot have friction. Electricity flows without resistance, because resistance is caused by electron collisions. If the electrons move in perfect unison, they do not collide. Particles behave less like rugged individuals and more like pieces of a single, continuous wave. And all of this comes from the simple fact that there is no thermal energy left to shake them out of this strange, unified order. But there is something even deeper hiding in this idea. If heat is motion, and motion is the primary evidence of change, then what happens to time in a place where motion is effectively gone? At the edge of absolute zero, when energy is reduced to the faintest whisper and atoms have been pressed into perfect stillness, time begins to look less like something that moves forward and more like something that simply is. It feels like a frozen landscape rather than a flowing river. Now, of course, we never quite get to total timelessness. The 0 point energy built into the quantum world prevents anything from being perfectly still. There is always a faint hum in the background, a quantum jitter. It serves as a reminder that even at the edge of nothingness, the universe refuses to be completely silent. But that hum is not the same as the noisy, violent motion we know at ordinary temperatures. It is the faint residue of existence itself. It is the smallest possible flicker of energy written into the fabric of reality. And this is what makes the end of heat so fascinating. Because it is not the end of matter, nor is it the end of physics. It is the place where our familiar picture of the world gives way to something hidden. It reveals a set of rules that only appear when energy has been stripped down to almost nothing. This is why scientists build their extraordinary cooling machines, lowering atoms to billionths of a degree above zero. They do not do this just to see how cold something can get that is just a number. They do it because every fraction of a degree peeled away brings them closer to this quiet world where the ordinary dissolves and the quantum takes over. In that quiet, they can watch the universe behave in ways that look more like thought experiments than physical reality. And yet, for all of its strangeness, this end of heat is not just an abstract concept. It shapes things in the world you live in right now. The microchips inside your phone rely on principles of electron behavior that were first discovered in these extreme conditions. Quantum mechanics, superconductivity, and the medical imaging technology of tomorrow all trace their roots back to this frozen edge of physics, where heat finally runs out of places to hide. And if this is what happens when energy fades to almost nothing, then the next step downward might be even stranger, because what lies just below this boundary is not just about temperature or motion anymore. It is about the fabric of existence itself. Now, we are moving into a place where the ordinary rules of the world fade away completely, and something stranger begins to speak. When heat drains out, when motion nearly vanishes, and when atoms settle into that eerie stillness near absolute zero, the quantum world stops hiding in the background. It steps forward, quietly, but relentlessly. And what it shows us does not feel like the world we know. It feels like something that was always there, waiting beneath the noise of temperature and motion, as if the universe itself has been whispering all along, but only in the kind of silence you find at the bottom of the cold. In our everyday lives, we do not notice quantum mechanics. It is not that it isn't there. It is just drowned out by everything else. It is buried by heat, by collisions, by the sheer chaos of trillions upon trillions of particles smashing around at once. That chaos acts like static on a radio, hiding the subtler music playing underneath. But as we approach absolute zero, the noise fades, the collisions slow, the clutter of motion falls away, and for the first time, the whispers underneath can be heard clearly. And those whispers are strange. They tell us that particles are not really solid, not really separate, and not really here or there in the way we understand location. They exist in overlapping clouds of probability. When you remove almost all of their thermal energy, those clouds expand. They begin to overlap until the distinction between this atom and that atom starts to blur. Instead of many things, you begin to see one thing. This is the world of quantum coherence, and it is most clearly revealed in that deep, frozen, dark. Here, atoms do not just share space, they share identity. When you cool a cloud of atoms to within a billionth of a degree of absolute zero, they collapse into that Bose-Einstein condensate, a single unified quantum state. It is not a metaphor for cooperation. It is a literal physical transformation. Those countless individual atoms move together as though they are one body. They stop behaving like independent particles and instead act like one enormous wave stretching across the entire system. You cannot point at one part and say, this is where one atom ends and the next begins, because there is no such boundary anymore. In this frozen darkness, quantum rules no longer compete with temperature. They dominate. And when they dominate, the world looks alien. Superfluids flow without resistance, ignoring the normal rules of friction. Superconductors carry electrical currents forever without a single bit of energy leaking away. And quantum tunneling, the phenomenon where particles slip through solid barriers that should be impossible to cross, becomes not just an occasional quirk, but an ever-present part of reality. This is why scientists build their elaborate cold traps and magnetic fields. Not because they want to conquer cold itself, but because they want to hear these whispers more clearly. They want to strip the world down until only the fundamental rules remain. And in that frozen silence, they find that the universe is not mechanical in the way we were taught to think. It is fluid, probabilistic, and deeply interconnected. What is even stranger is how this frozen quantum world touches our everyday lives, even if we never see it directly. The processes inside your computer, the sensors in your camera, the lasers used in eye surgery, all of them exist because we have learned how to listen to those whispers. Without the study of absolute zero, or at least the journey toward it, we would never have learned how to bend quantum mechanics into something we can use. But it is not just technology that hides here. There is something deeper, something almost philosophical in the way the quantum world emerges from the cold. Because if you think about it, what we are really watching in these experiments is not just matter-changing state. We are watching reality itself change its behavior. We are seeing what happens when the universe's most hidden rules are allowed to speak without interruption. And the deeper we go, the quieter it gets. Not quieter in the sense of silence you can hear with your ears, but quieter in a way that feels almost unnerving, because this is the silence where nothing moves unnecessarily, where nothing happens by accident, where every remaining trace of energy is dictated not by chaos, but by rigid structure. The world becomes simpler, sharper, and almost unnaturally perfect. And yet, it is not truly still. 0-point energy remains that faint, unavoidable hum of motion that even the universe cannot erase. That hum is important. It is a constant reminder that there is no absolute emptiness. Even in this frozen dark, the universe never fully stops. Instead, it balances on the precarious edge between motion and stillness. We find ourselves in a kind of suspended state where everything you thought was separate begins to feel strangely connected. The more you stare at this domain, the more it begins to feel like absolute zero is not really about temperature at all. It is about stripping the world down to its rawest, most fundamental form. And if these are the whispers we can hear in this place just above the bottom of the scale, then the question becomes, what else is waiting in this frozen world just out of reach? Because we are not done descending. Not yet. There is still more hidden beneath this quiet. If we keep going, pushing past the boundaries of what seems possible, we might just see how even entropy itself, the chaos that drives the universe, starts to rest. This is where the descent stops feeling theoretical and starts becoming something you can almost see with your own eyes. At these temperatures, just a breath above absolute zero, matter itself changes into something so strange, so quiet, and so unlike anything we know from our daily lives that it hardly feels real. This is the home of the Bose-Einstein condensate, a place where particles stop being separate things and begin to merge into a single, ghostly state. To understand how radical this is, we must look at the world we usually inhabit. Under normal conditions, every atom acts as its own little world. It spins, it vibrates, it moves through space, and it keeps to itself. Even when you pack atoms tightly into a solid block of iron or a crystal of salt, each atom remains an individual, jostling and bouncing in its own private space. Heat is the fuel for this individuality. The constant thermal motion scrambles them, ensuring they remain distinct and separate. But near absolute zero, the heat that fights for their independence is stripped away. Motion slows, energy drains, and what is left behind is not just colder, it is simpler. When matter reaches this extreme edge of cold, quantum mechanics, the deep, invisible set of rules that normally hides underneath the noise of the everyday world starts to take over. And when it does, atoms stop behaving like distinct billiard balls. They spread out. They blur into waves of probability. As the cold deepens, those waves expand, overlap, and begin to lock into place with one another. It is no longer a million separate things. It becomes one thing, a Bose-Einstein condensate. This state of matter is unlike any other in the universe. Imagine a crowded room full of people. In the ordinary world, everyone is talking, moving, and thinking their own thoughts. It is chaotic and diverse. That is matter at ordinary temperatures. Now, imagine that somehow every single person in that room stops moving, stops speaking, and begins to act with one perfect shared purpose. They breathe in unison. They move in unison, not because they have been ordered to, but because the very rules of existence demand it. That is what happens inside a Bose-Einstein condensate. Millions of atoms surrender their individuality to merge into a single quantum identity. They move as one. They exist as one. You can no longer tell where one atom ends and another begins because, in a very real physical sense, they have stopped being separate things at all. When this idea was first predicted, it sounded like fantasy. In 1924, the Indian physicist Satyendra Nath Bose sent a paper to Albert Einstein proposing a new way to count particles. Einstein extended the idea, calculating that if a gas of certain particles were cooled far enough, they would all collapse into the same lowest energy state. But at the time, this was purely a mathematical dream. There was no technology on Earth capable of reaching such freezing depths. It was a theory waiting for reality to catch up. It wasn't until 1995, over 70 years later, that scientists finally created the first Bose-Einstein condensate in a laboratory. By using lasers and magnetic fields to trap and cool a cloud of rubidium atoms to just a few billionths of a degree above absolute zero, they achieved the impossible. And when they looked at the data, the image they saw was exactly what Bose and Einstein had described: an entirely new state of matter that moved like a single, unified ghost. The word ghostly is not an exaggeration. When you peer into a Bose-Einstein condensate, you do not see a collection of hard, distinct particles anymore. You see a single, smooth entity, a shimmering cloud where every atom is perfectly synchronized with its neighbor. It is as if matter has stopped arguing with itself and decided, for once, to act in perfect harmony. But the strangeness doesn't stop there. In this ghostly state, matter acquires superpowers that sound impossible in the ordinary world. A Bose-Einstein condensate can flow without friction, sliding over surfaces forever. It can interfere with itself like a wave of light, creating patterns of ripples from a single source. It can even exist in overlapping states, where the difference between here and there starts to lose its meaning. This is not the kind of matter that builds walls, coffee mugs, or car engines. This is matter stripped down to its most fundamental, most unreal behavior. It is a glimpse of what the universe is made of when it is quiet enough to listen. And yet, even though this sounds abstract, this ghostly state is not just a curiosity locked in a laboratory. It is a key to understanding the deepest rules of reality. When scientists study Bose-Einstein condensates, they are not simply learning about cold atoms. They are learning how quantum mechanics works on a scale large enough to be seen. They are observing how particles interact when individuality disappears. Some physicists even believe this state mimics how the early universe might have behaved in its very first moments, when everything was packed into a single, uniform state before the Big Bang unleashed the chaos we know today. Because in a strange way, a Bose-Einstein condensate is a kind of echo of the beginning. When you cool matter this far down, you are forcing it into a state of almost perfect order, a state that might resemble what the universe looked like before motion, before heat, and before complexity took hold. It is as if by chasing absolute zero, we are not just exploring the edges of temperature, but brushing against the edge of time itself. And that is why this ghostly state matters. It is not just science for its own sake. It is a reminder that buried beneath our familiar world of warmth, friction, and movement is a quieter, stranger universe that only reveals itself when everything else has been stripped away. But we are not done yet. Because if Bose-Einstein condensates show us what happens when matter unites, the next step downward will show us what happens when even entropy, the great engine of disorder, finally begins to rest. This is where the silence of the cold deepens into something even stranger. We have seen how atoms slow, how matter merges into a single ghostly state, and how the familiar world begins to dissolve into something quieter and more unified. But if we keep going, if we imagine ourselves moving even closer to absolute zero, we come face to face with a concept that has always been tied to the arrow of time itself, entropy. And here, at the edge of the frozen dark, we begin to see what it looks like when entropy almost stops. Entropy is usually the great, unstoppable tide of the universe. It is the tendency for things to drift from order to disorder, for neatness to unravel, and for heat to spread out until everything is evenly dull and quiet. It is the reason a drop of ink disperses in a glass of water and never gathers itself back into a droplet. It is the reason broken cups do not leap off the floor and reassemble themselves. And it is why time, as we experience it, always seems to move in one direction. Entropy grows, disorder spreads, and we move forward with it. But near absolute zero, entropy is brought to heel. When you cool a system to the edge of this unreachable temperature, something happens that does not occur anywhere else in nature. The random motion that fuels disorder fades. The collisions that scramble energy and scatter it into every corner of the universe nearly vanish. Instead, everything locks into place. Atoms line up in their lowest energy states, with no room left to fall any further. The chaotic shuffling of heat is replaced by an eerie stillness where there are no more moves left to make. This is why scientists sometimes describe absolute zero as the point where entropy reaches its minimum. It is not zero entropy, not quite, because quantum mechanics will not allow that. That faint hum of zero-point energy is still there, the tiny, irreducible vibration of a universe that can never fully stop. But compared to the restless storm of ordinary matter, it is almost nothing. It is as if all the disorder has been drained away, leaving only a quiet, perfectly arranged structure. Matter is as close to absolute order as the laws of physics will ever allow. And here is the astonishing part. This is not just theoretical philosophy. In the laboratory, when scientists cool materials to billionths of a degree above absolute zero, they can watch entropy's grip loosen. They see particles falling into alignment, energy levels narrowing until everything behaves as if the universe itself has taken a deep, steady breath. A cloud of atoms, once a mess of random motion, collapses into that unified wave. Superconductors switch on and begin conducting electricity with flawless efficiency. Superfluids start sliding without friction forever. These are not just experiments. They are glimpses of a world where entropy no longer dominates. But what is even more unsettling is what this implies for time itself. If entropy is tied to the arrow of time, if the increase of disorder is what gives us a sense of past and future, what does it mean to reach a place where entropy has nowhere left to climb? In this deep, frozen stillness, time feels less like a rushing current and more like a frozen lake. Events stop tumbling over one another. They simply hold. It is not that time disappears, but its movement loses the urgency we are used to. In this strange world near absolute zero, the universe looks less like it is rushing forward and more like it is paused, hovering on the edge of motion and change. Yet, even in this pause, the faint hum of quantum mechanics remains. And that hum matters deeply, because if entropy could truly reach zero, If disorder could be erased completely, everything would be locked forever, with no possibility of change. The universe would become a perfect crystal of eternal stillness. But that never happens. There is always that whisper of energy, that trace of motion, that reminder that nothing in this universe can be perfectly frozen. And maybe that is what keeps the story going. Because without that faint hum, there would be no time, no change, no future, nothing at all. So entropy never truly dies. It only slows. It waits in this deep quiet, reduced to its barest form, like a candle's last ember glowing in an endless night. And in that stillness, we see what the universe is built on, a delicate balance between the relentless pull of disorder and the silent boundary that holds it back. But as strange as this frozen calm is, it is not the end of our descent. Even here, at the very edge where entropy rests and disorder fades, there are deeper questions waiting to be asked. What happens to time itself when the universe is this still? What does it mean for energy, for matter, and for the very nature of reality when everything sits this precariously close to the edge of nothingness? If there is anything that has been hiding quietly behind all of this, beneath the slowing atoms, beneath the vanishing heat, beneath entropy itself, it is time. We live our entire lives swept up inside its current. It pushes us forward, relentless and indifferent, whether we want it to or not. It shapes our days, measures our years, and gives our world a distinct before and after. But down here, near the bottom of the thermometer, time does not feel the same. It does not flow with the same urgency that it does in the world of warmth and motion. It hangs differently, stretched and quiet, like a note of music that has been muted almost to silence. We must remember that time, as we usually perceive it, depends entirely on change. We mark its passage by events, clocks ticking, the earth rotating, hearts beating, particles colliding and exchanging energy. But at temperatures near absolute zero, change slows almost to a halt. The atoms that once danced furiously are reduced to their lowest energy states, their motion so faint it is barely there at all. If you could stand here, not in a physical sense, but in the way the mind imagines standing in a landscape, you would find yourself in a kind of suspended world. It is a place where the usual rhythm of events has been thinned to its barest, most fragile thread. And that raises a strange, unsettling question. If almost nothing moves, does time still matter? Or does it just sit here too, waiting for something, anything, to happen? Physics has an answer, though it is not the one that makes our intuition comfortable. Time does not disappear, but it becomes abstract. At these temperatures, what we call time is no longer a steady tick-tock valid for every observer everywhere. Instead, it becomes tangled with energy, with motion, and with quantum rules that stretch and bend the way we usually understand chronological order. Near absolute zero, the line between then and now grows dangerously thin. Events stop piling on top of one another in the usual, orderly sequence. It is as if time, at least in this domain, has less work to do. Quantum mechanics makes this even stranger. Down here, where particles overlap and form single unified states, the usual notion of cause and effect starts to blur. When millions of atoms merge into a Bose-Einstein condensate, they stop acting like individual things moving through time one by one. Instead, they behave like a single quantum wave, existing all at once in one vast shared state. In that wave, time isn't something you measure from particle to particle. It is something that stretches across the whole system at once, as though the usual mechanical clock we use to count it has been replaced by something slower, softer, and less local. This is not just theory scrawled on a blackboard. Experiments have shown that near absolute zero, certain processes that normally tick away with perfect regularity can stall. Chemical reactions that would happen in the blink of an eye at room temperature crawl almost to nothingness. Even quantum fluctuations, the jittering, unpredictable background activity of the universe, quiet down until they are barely detectable. It is not that time has vanished. It is that it has been emptied of its usual urgency, leaving only a long, frozen moment where almost nothing happens at all. But here is where it becomes even more philosophically unsettling. If time slows this much for matter in this frozen state, what does that say about the deep connection between time and heat itself? If the arrow of time is tied to entropy, the tendency of the universe to spread out and unravel, what happens in a place where entropy has been brought to a near stop? Some physicists have speculated that in these frozen conditions, time might not be something that flows independently at all. Instead, it might simply be a measure of change. And when change almost disappears, time effectively pauses. This does not mean that time dies at absolute zero. Even here, 0-point energy, the faint, unkillable hum of quantum motion remains. And that hum carries with it just enough activity to keep the universe from locking into perfect stillness. In a way, that leftover motion is what keeps time alive. Without it, there would be no difference between one moment and the next, and no reason to say that anything happens at all. Maybe that is the most fascinating thing about this frozen edge of existence. It does not erase time. It exposes it. It strips away the decorations. It shows us that time is not a universal stage running in the background. It is a property that depends on motion, energy, and change. Strip those things away, and time thins out like the air at the top of a mountain until only the barest trace of it remains. If this is what happens to time near absolute zero, then what we are about to see next goes even further. Because now we reach the question that scientists have been chasing since the beginning. Can absolute zero itself ever truly be reached? Or is it a horizon that will always retreat no matter how far we go? We have been sliding further and further down the thermometer, peeling away motion, draining heat, and quieting the restless chaos of matter. And now we have arrived at the edge of the coldest idea there is: absolute zero. A temperature so low it feels less like a number and more like a wall in the fabric of reality. But here is the catch. Can we ever actually reach it? For centuries, the idea of absolute zero has tempted physicists almost like a dare written into nature itself. The number is clear: minus 273.15 degrees Celsius, or 0 Kelvin, the end of heat. But if you try to get there, you discover something strange. The closer you move toward it, the more it pushes back. It is as though the universe has hidden it behind an infinite series of locked doors. The reason is rooted in one of the most unyielding laws of physics, the third law of thermodynamics. This law effectively says that as you approach absolute zero, the amount of energy you need to remove in order to cool something further increases without limit. Each fraction of a degree costs more work than the last. At first, cooling is simple. Take a warm object, put it in a freezer, and it gives up its heat easily. But as you move down the scale, that heat becomes harder to extract. The particles cling to their last traces of motion, and stripping away that final sliver of energy becomes an impossible task. It is like chasing a horizon. You can walk toward it forever. You can keep getting closer and closer, but you never quite touch it. You can slow atoms until they are moving so faintly that their behavior almost stops resembling anything familiar. You can cool the system to billionths of a degree above zero. But the last step, the one that would take you all the way to the bottom, is forever out of reach. And even if you could somehow take that step, quantum mechanics would stop you. Because down here, near the bottom of the scale, 0-point energy begins to matter. It is the lowest level of energy that even the coldest object cannot lose. No matter how hard you try, you cannot erase it. It is built into the very fabric of reality. Even if everything else went still, that subtle vibration would remain, keeping the universe from ever truly freezing into a state of zero motion. But that does not mean our journey down the scale is pointless. Far from it. Even if absolute zero itself is unreachable, the pursuit of it has led us to some of the most astonishing discoveries in physics. The quest to get closer has created states of matter that do not exist anywhere else in the natural universe. Bose-Einstein condensates, superfluids, superconductors, these are not just scientific curiosities. They are proof that as you move closer to this limit, reality begins to peel back its layers and show you what has been hiding underneath all along. And the technology we have built in this chase has reshaped the world. We have created laboratories where lasers and magnetic traps can chill atoms until they are slower than anything that naturally exists in the cosmos. We have cooled matter to temperatures colder than the empty vacuum of deep space. And in those places, we have learned how quantum mechanics truly behaves when heat no longer overwhelms it. But this unreachable horizon, this absolute zero, is not just a frustration. It is also a gift, because it sets the boundary that defines everything else. Without it, temperature would have no meaning. Heat would have no bottom, only a direction we couldn't measure. Absolute zero is the anchor, the limit that keeps the scale of energy grounded. Even if we can never touch it, its presence shapes everything above it. And, in a way, there is something comforting about that. It means there will always be one more step we can take downward. Always another fraction of a degree to reach. Always another discovery waiting in that vanishing space between the world we know and the horizon we cannot cross. And maybe that is the real point of science itself. Not to arrive, but to keep getting closer. To keep stripping away the noise until the universe shows us what it looks like when it is as quiet as it can possibly be. Because while we may never truly reach absolute zero, every step toward it teaches us something profound about the nature of reality itself. Our journey is not just about coal or energy, or even the strange vocabulary of quantum mechanics. It is fundamentally about the way the universe protects its deeper secrets, offering them up only one fraction of a degree at a time. But now that we understand why this limit can never be broken, we must turn to the next logical question. What exactly is enforcing it? What physical law holds that boundary in place and keeps absolute zero forever out of reach? This is where we meet the law that draws the line in the cold. We have been following temperature as it drains away, watching motion slow down and energy fade into the background. But if you want to know why absolute zero always remains just out of reach, this is the moment where the mechanism reveals itself. It is not a matter of bad luck. It is not a flaw in our engineering or a limitation of our machines. It is the third law of thermodynamics, nature's unbreakable rule. The third law does not shout the way the other laws do. The first law is bold. It tells you that energy cannot be created or destroyed, establishing the fundamental currency of the universe. The second law is relentless. It gives you entropy, that unstoppable drift toward disorder and decay. But the third law is quieter. more subtle. It simply tells you that as a system approaches absolute zero, the amount of work needed to cool it the rest of the way grows without limit. It implies that you can step halfway to the goal and then halfway again, but the number of steps is infinite. It does not matter how clever you are, how massive your budget is, or what futuristic technology you invent. Nature will always add one more wall between you and that last degree. This is not just an abstract theory scrawled on a blackboard. You can see it in every experiment ever conducted. The first steps downward from room temperature are deceptively easy. You can cool something with ordinary ice, then switch to dry ice, then to liquid nitrogen, and eventually to liquid helium. The temperature drops quickly, plunging hundreds of degrees with manageable effort. But as you keep going, passing into the realm of kelvins and millikelvins, the game changes. Each fraction of a degree takes exponentially more effort than the one before it. It is like trying to drain a glass of water, only to find that no matter how much you pour out, there is always a thin film of moisture left clinging to the sides, refusing to leave. That final trace of energy is stubborn. It clings to matter with a grip that tightens the colder it gets. This happens because of entropy. As we discussed, near absolute zero, a system's entropy, its measure of disorder, approaches a minimum constant value. All the particles settle into their lowest energy states, and there is nowhere left for them to go. The random jostling that normally allows heat to flow out simply stops happening, and if there is no randomness left to drain, the process of heat removal becomes incredibly difficult. You can push the system closer and closer to that perfect order, but you will never erase that last sliver of motion entirely. And here is where quantum mechanics steps in, making the third law even more absolute. Even in this deep freeze, there is 0-point energy. This is the unavoidable hum of the quantum world, the vibrating floor of the universe. It is what keeps atoms from being perfectly still, no matter how powerful your cooling methods are. You cannot take that hum away because it isn't heat. It is not something you can remove like a stain. It is a built-in feature of reality itself, woven into the fabric of existence. This is why scientists describe absolute zero as a limit, not a destination. You can get closer than you ever thought possible. You can get to within 1/1000th of a degree above it, colder than the deepest voids between galaxies, but you will never touch it. The law will not bend. And yet, the irony is that the impossibility of reaching absolute zero is exactly what has driven some of the greatest achievements in physics. Cryogenic laboratories all over the world have turned this uncrossable limit into a challenge. They have developed techniques that seem to defy logic. They use laser cooling, a method that sounds counterintuitive, using light, which carries energy, to cool things down. By tuning lasers to a precise frequency, scientists can bombard atoms with photons that hit them head-on, slowing their motion just like a stream of ping-pong balls slows down a rolling bowling ball. This creates a substance known as optical molasses, a thick, viscous field of light that traps atoms in a slow-motion crawl. They use magnetic traps, invisible cages made of magnetic fields that hold these sluggish atoms still, preventing them from touching the warm walls of the container. And they use evaporative cooling, a process similar to blowing on a hot cup of coffee. By lowering the walls of the magnetic trap, they allow the fastest, hottest atoms to escape, leaving the colder, slower ones behind. Each method chips away at motion, pushing matter closer and closer to that forbidden boundary. And each time we get nearer, the universe rewards our persistence by showing us something new. Without the third law forcing us to innovate, we would never have discovered superconductivity, that miraculous state where electricity flows without resistance. we would never have seen Bose-Einstein condensates, where matter stops behaving like a cloud of individuals and starts behaving like one seamless entity. We wouldn't have learned that friction can vanish, that entropy can stall, and that time itself seems to blur when motion almost disappears. But this law also says something profound about the architecture of the universe. It tells us that there are limits we can approach but never cross. It tells us that perfection, in this case, the perfect stillness of absolute zero, exists only as a conceptual boundary, not a physical destination. The universe allows you to move closer and closer, but it always keeps one last step beyond reach, as if reminding you that there is always something left to chase. And maybe that is the most beautiful part of it. The third law doesn't just stop us, it shapes the way we explore. It forces us to look at what happens in that narrowing space between what is possible and what is forbidden. It is in that thin, frozen gap that we have made our greatest discoveries. And if this is the limit the third law sets, then the next step is clear. We need to stop worrying about the destination and start looking at the scenery just before the end. We need to see what happens in that space just above the impossible, because this is where matter stops behaving like matter at all. Now we are stepping into the part of the cold where the familiar rules of the universe start to warp. We have seen how the third law of thermodynamics builds an unbreakable wall around absolute zero. But even just a breath above that wall, physics no longer behaves the way it does in the world we know. Here, near the bottom of the thermometer, matter stops following the logic of everyday experience. It begins to twist, stretch, and bend into forms that feel almost impossible, and yet every bit of it is real. At room temperature, physics is comforting and predictable. Objects have clear, rigid boundaries. Heat moves predictably from hot to cold. Particles bounce and collide like tiny billiard balls in a game we intuitively understand. But as you cool things down, you strip away that ordinary behavior layer by layer until nothing familiar is left. This is where the quantum world takes over completely. And what you find there is a catalog of phenomena that exists nowhere else in the cosmos. One of the strangest and most revolutionary is superconductivity. In the world of ordinary temperatures, electrical resistance is an unavoidable fact of life. When you run a current through a copper wire, the electrons carrying that current have a difficult journey. They scatter against the vibrating atoms of the copper, crashing into obstacles and wasting energy as heat. It is like trying to drive a sports car through a crowded city during rush hour. You stop, you start, you burn fuel, and things heat up. But as you lower the temperature, that scattering begins to fade. If you cool a material enough past a specific critical temperature, something extraordinary happens. Its resistance doesn't just decrease, it vanishes. It drops to zero. Suddenly, the electrons are no longer fighting their way through a crowd. They begin to pair up, forming what are called Cooper pairs. These pairs move together in perfect synchrony, gliding through the material without ever colliding, without losing energy, and without stopping. They flow forever, as if friction itself has been erased from the rule book of the universe. Then there are superfluids, those eerie substances that appear when certain liquids, like helium-4, are chilled to a fraction of a degree above absolute zero. In this state, the liquid stops behaving like a normal fluid. It loses all viscosity. If you stir a cup of superfluid helium, it will not swirl for a few seconds and stop. It will swirl forever. It flows effortlessly through narrow channels and around obstacles without slowing down. It can even do things that seem to violate gravity. A superfluid can creep up the sides of its container, climbing the walls in a thin film, and spill over the edges to drip down the outside. It does this not because of pressure or magic, but because in this bizarre world near absolute zero, the usual forces that keep liquids in their place no longer apply. The fluid seeks a state of equilibrium with such persistence that it will walk up walls to find it. And if that isn't strange enough, this is also where we find those Bose-Einstein condensates we touched on earlier. Those ghostly clouds of atoms that merge into a single quantum state. In this condition, matter behaves as if individuality no longer exists. Millions of atoms collapse into perfect harmony, acting like one vast, unified particle. In this frozen domain, the difference between many and one stops mattering. The cloud is no longer a collection of parts. It is a single wave function, a single entity sharing one existence. But these phenomena are just the beginning. The deeper you explore this frozen frontier, the more exotic the landscape gets. Quantum tunneling, the phenomenon where particles slip through barriers they should never be able to cross, becomes increasingly significant. At room temperature, if you throw a ball at a wall, it bounces back. In the quantum world, if you throw a particle at an energy barrier, there is a chance it will simply appear on the other side, as if it teleported through the solid obstacle. Near absolute zero, this isn't a rare exception anymore. It becomes a dominant way the world behaves. Particles stop caring about boundaries. They move in ways that defy every instinct we have built from living in a warm, noisy universe. Even time itself starts to feel strange here. At these temperatures, the slowing of motion and the reduction of entropy create an environment where events no longer unfold at the same pace we are used to. Processes that would normally happen instantly, chemical reactions, particle interactions, are drawn out. They are slowed until they almost appear to hold their breath. The universe down here is not gone, but it is suspended, like a single quiet frame stretched across a canvas of stillness. What is truly remarkable is that we have actually learned how to reach this frozen edge of physics in the laboratory. Scientists have cooled atoms to billionths of a degree above absolute zero, trapping them with lasers and magnetic fields in the center of vacuum chambers. And in that deep freeze, they have seen the laws of nature flex in ways that textbooks once only imagined. They have turned ordinary gases into quantum clouds, watched fluids lose their friction, and made electrons flow endlessly, never tiring, never slowing down. This bending of physics near absolute zero isn't just a curiosity or a parlor trick. It is a window. It shows us what the universe looks like when the usual layers of thermal chaos are stripped away. It is a glimpse at reality without the noise of heat and motion. It is pure, undistorted behavior, governed only by the most fundamental laws of existence. And when we look through that window, we realize that the world we live in, the warm, messy, moving world, is actually the exception. The real, underlying order of things is waiting down there in the cold. But perhaps the most extraordinary thing about this realm is not just the mechanics, but what they imply about reality itself. If the universe can bend this way in the cold, if matter and energy can transform so completely just by removing the agitation of heat, what else might be hiding down here? What other rules might emerge when we push closer to the ultimate limit? We are now entering one of the strangest, most mesmerizing regions of the cold, where matter stops behaving like anything you have ever seen before. This is where superfluids live. These are impossible liquids that flow without friction, climb walls, and move forever without losing an ounce of energy. They are not just a scientific curiosity to be noted and forgotten. They are physical proof that the universe has hidden rules, an entirely different operating system that only reveals itself when you press reality down toward the bottom of the thermometer. At first glance, a superfluid does not look like anything extraordinary. Take liquid helium, for example. If you chill it down to just a few degrees above absolute zero, it behaves like any other liquid. It looks like water. It sloshes around in its container. It has waves and bubbles. It possesses viscosity, which is the internal friction that makes fluids thick and resistant to pouring. Honey has high viscosity. Water has low viscosity, but even water resists motion. If you stir it, it eventually stops because its molecules rub against each other, losing energy to heat. But if you cool that helium further, pushing it right to the edge of that frozen frontier, specifically to a point known as the lambda point, everything changes. In a split second, the helium undergoes a violent, then silent transformation. It stops acting like a liquid. Its viscosity vanishes completely. It becomes a superfluid, and from that point on, it moves in ways that seem to defy reason. You can pour it into a glass container, and it won't just sit there. It will form a thin film that creeps up the walls, defying gravity, and spills over the edge to drip off the bottom. It does this not because it is being pushed, but because it is seeking equilibrium with zero resistance to hold it back. You can stir a cup of superfluid helium, and the vortex you create will spin forever. Literally forever. There is nothing left to slow it down. No friction, no resistance, no loss. It is as if the very concept of stopping has been erased from the liquid's vocabulary. The explanation for this strange behavior is not hidden in the macroscopic world of ordinary liquids. It is buried deep in quantum mechanics. At these temperatures, the helium atoms lose their individuality. They overlap and lock together into a single, unified quantum state, just like in a Bose-Einstein condensate. Instead of moving independently, like a chaotic crowd, they move collectively, like a disciplined regiment. The whole liquid flows as if it were one single entity, and because of this perfect quantum alignment, there is no scattering, there is no internal friction to dissipate its motion. The result is a liquid that can flow endlessly, not because it has an infinite energy source, but because at this scale, there is no mechanism left to create loss in the first place. This frictionless flow is not just an odd laboratory trick. It changes how we see the fabric of matter itself. It shows us that in the deep cold, the universe is capable of sustaining states of perfect efficiency. These are states that make our ordinary world of resistance, heat waste, and friction look crude and broken by comparison. And it does not stop with helium. The same principle that creates superfluids also helps explain superconductors, those materials that carry electric current forever without resistance. Different systems, same rule. Near absolute zero, motion stops being messy. It becomes perfect. And there is something strangely hypnotic about that idea. Consider our daily existence. We live in a universe defined by loss. It is the tragedy of thermodynamics. Push a swing, and it eventually slows down. Roll a ball, and it stops. Run electricity through a wire, and heat bleeds away, wasting energy. Every action we take fights against friction and decay. But down here, in the silence near absolute zero, those rules are suspended. Push a superfluid, and it never slows. Create a current in a superconductor, and it will circle endlessly, potentially for the lifetime of the universe. In this frozen domain, perfection is not just theoretical, it is real. But there is a deeper implication hiding in this. If friction can disappear in these conditions, if matter can move endlessly without wasting energy, then what does that say about the limits of the physical world? Does this mean that the universe, in its most stripped-down form, has no natural reason to decay? Is friction not a fundamental feature of nature, but only a symptom of heat and chaos? When you strip all of that away, you find a level of order that feels almost alien. And yet, this alien order is not out of reach. We have touched it. We have created superfluids and watched them climb the walls of their beakers, behaving like no ordinary liquid should. We have built superconducting magnets that power MRI machines and particle accelerators, carrying currents that do not fade. These are not just experiments. They are glimpses into what matter looks like when it sheds the limitations of our warm, disorderly world. But the closer we get to this perfection, the more it feels like we are peeling back a layer of the universe that was never meant to be visible. Superfluids and superconductors serve as reminders that beneath the noise of heat, the universe hides a kind of flawless rhythm, a state where things no longer resist or decay. And if that is what lives here at the edge of the cold, then we have to wonder what else might be hiding just a fraction of a degree further down. What happens if we follow this descent out of the laboratory and into the wild until we reach the faintest hum of motion left in the universe? While we have been following absolute zero downward in our machines, the universe has been holding its own frozen secrets in the vast dark between the stars. Space, for all its emptiness, is not truly empty. It has a temperature, and that temperature, just a few degrees above absolute zero, is the quiet backdrop against which everything else exists. It is the cosmic floor, the coldest natural stage in all of reality. And if we want to understand what absolute zero really means on a grand scale, this is where we need to look. When you step out of the warmth of planetary atmospheres, away from the burning fusion of stars, and into the deep interstellar void, you find yourself surrounded by a darkness so complete it feels almost physical. There is no sunlight here. There is no warmth bleeding from familiar worlds. There is only the dim afterglow of the Big Bang itself. This energy has been stretched thin over billions of years as the universe expanded, cooling down until it measures just 2.7 Kelvin. That is negative 455 degrees Fahrenheit. This is the temperature of the cosmic microwave background. It is a faint, ever-present sea of radiation left behind from the moment the universe was born. It has been fading for nearly 14 billion years, and now it is the quiet temperature that fills the universe from one edge to the other. This means that if you were to float out there, far from every star, you would be surrounded by a cold so deep it would make any winter on Earth seem like a furnace. And yet, even this is not truly absolute zero. Space itself, in all its vast emptiness, is still a little too warm to be perfectly still. That lingering microwave glow, those tiny photons left over from the dawn of time, keep the universe from reaching the absolute bottom of the scale. Even in the farthest, darkest corners of the cosmos, there is still motion. There is still energy. But there are places out there that come remarkably close. Near the shadowed edges of interstellar clouds, those massive nebulas where dust and gas gather in lightless knots, temperatures drop even lower than the background of space. In regions like the Boomerang Nebula, expanding gas cools itself down to just a fraction of a degree above absolute zero. These are some of the coldest natural regions in existence. They are cosmic laboratories where matter slows to an almost perfect hush. Here, molecules move so slowly that they can stick together in delicate clusters. If it were any warmer, these fragile chemical bonds would shatter. But in the quiet, they survive, building the first pieces of new stars and planets. It is a kind of frozen womb for creation, where the absence of heat becomes a necessary space for building complex things. And then there are the even stranger places around the graveyards of stars, neutron stars, and black holes. Here, gravity bends everything, including light and time itself. In the deep shadow of these collapsed giants, theories suggest there are regions so drained of energy that their temperature dips nearly to nothing. And yet, even there, absolute zero refuses to appear. Quantum mechanics stands guard. 0-point energy, that faint hum built into the vacuum of the universe, keeps everything from ever truly stopping. It is as if reality has a rule that says nothing, not even the coldest, deadest corners of space, can be perfectly still. This is what makes absolute zero such a haunting idea. It is not just an unattainable number on a scale. It is a boundary that exists everywhere, interwoven with the fabric of the cosmos. No matter how far you go from the stars, no matter how deep into the black you drift, you will never touch it. You will only brush against it, feeling it in the silence of those last degrees where matter almost forgets how to move. And yet, those places, those nearly frozen regions of space, are not lifeless. They are not meaningless voids. They are where the universe slows down enough for us to glimpse what it is truly made of. They are where astronomers look when they want to study the chemistry of the early cosmos. Because only there, in that deep, frozen dark, can the most fragile molecules survive long enough to tell their story. In a strange way, these places are a bridge between what the universe was and what it is becoming. But perhaps the most fascinating and somber thing about this cosmic cold is what it implies about the future. Because the universe is changing, it keeps expanding, it keeps cooling, it keeps spreading its energy thinner and thinner across the void. Stars have finite fuel. They will eventually burn out. Galaxies will dim. The restless motion of everything will fade. One day, billions upon billions of years from now, all of space will sink closer and closer to absolute zero. This is the theoretical heat death of the universe. It is not a fiery end, but a quiet one, a slow, gentle fade into the dark. The stars will be gone. The black holes will eventually evaporate. The chaotic energy that defines life and movement will be smoothed out until the entire cosmos is nothing but a thin, cold whisper of what it once was. And if that happens, we will finally see what absolute zero looks like on the grandest scale imaginable. Not in a laboratory, not in a single droplet of helium or a trapped cloud of atoms, but across everything. A universe frozen to the edge of stillness, a horizon of cold without end. Let us step back from the silent emptiness of deep space and return to a place that is, in many ways, even stranger. We are entering our own laboratories here on Earth, places where scientists have learned how to push matter closer to absolute zero than anywhere else in the known universe. These are not just rooms filled with expensive equipment. They are modern-day cathedrals of precision, built to strip away motion one fraction of a degree at a time, until the ordinary world disappears and the hidden rules of reality start to show themselves. When you walk into one of these laboratories, you might expect to see a scene from a science fiction movie. Frost coating the walls, clouds of frozen air swirling around scientists in heavy parkas. But absolute cold does not look like the movies. It looks like silence. It looks like control. What you will find are chambers of polished stainless steel, vacuum pumps humming quietly in the background, lasers so precise they can push on individual atoms, and magnetic traps that hold matter in place as if gravity itself had been rewritten. These are the tools of the coldest science on Earth. The process begins by removing heat in the simplest way imaginable, by isolation. First, scientists pull almost all the air out of a chamber, creating a vacuum so empty it makes the space between planets look crowded. Without air, there are no stray molecules to collide with the experiment and warm it up. Then, they use liquid nitrogen at 77 Kelvin and liquid helium at 4 Kelvin to draw the temperature down further. This is where most everyday intuition about cold ends. To us, liquid helium is unimaginably cold. But for these labs, it is only the starting line. From there, the descent slows, because each step closer to absolute zero becomes exponentially harder. Conventional refrigeration stops working. To go lower, scientists must use light. Lasers are used next, not to heat things up, as we usually expect lasers to do, but to cool them down. By tuning a laser to a very specific frequency, slightly below the resonance of the atoms, scientists can bombard the atoms with photons. Think of an atom as a bowling ball rolling toward you. If you throw thousands of ping pong balls, photons at it, each tiny impact will slow the bowling ball down just a little bit. If you do this from all 6 directions, up, down, left, right, front, back, you create a zone of optical molasses where the atoms are trapped in a slow motion crawl. This technique, known as laser cooling, has brought atoms to temperatures within billionths of a degree of absolute zero. It creates a place so cold it does not exist anywhere naturally, not even in the deepest, darkest voids of interstellar space. But it doesn't stop there. Even laser-cooled atoms are too hot for the ultimate experiments. Once the atoms are slowed, magnetic and optical traps hold them in place, preventing even the smallest stray vibrations from the outside world from warming them again. And then, through a process called evaporative cooling, scientists perform the final trick. It is exactly the same principle as blowing on a hot cup of coffee to cool it down. The hottest atoms, the ones moving slightly faster than the rest, are allowed to escape the magnetic trap. When they leave, they take their excess energy with them, lowering the average temperature of the atoms left behind. With every step, the remaining cloud of atoms grows quieter, calmer, and more synchronized, until finally, what is left is no longer just matter as we know it. It is something new. This is how Bose-Einstein condensates are born. It is how we have created superfluids in controlled settings, watched superconductivity unfold in real time, and studied quantum mechanics on a scale big enough to see with cameras. These laboratories are the closest thing we have ever built to a window into another version of the universe, one where heat, motion, and even time seem to loosen their grip. But this isn't just about pure curiosity or philosophical satisfaction. These experiments have reshaped the technology you use every day. MRI machines in hospitals rely on superconducting magnets that must be kept at cryogenic temperatures to work. Quantum computers, which promise to revolutionize everything from medicine to encryption, operate in dilution refrigerators near absolute zero to protect their fragile quantum states from thermal noise. Ultra-precise atomic clocks, which keep the world's GPS systems synchronized, owe their accuracy to the techniques developed to cool and trap atoms. By chasing the lowest temperatures, scientists haven't just revealed the foundations of reality, they have started building tools that rely on those foundations. And yet, no matter how far they push, the third law of thermodynamics still stands in the way. Absolute zero remains unreachable, a horizon that mocks every achievement. But here is the beautiful paradox. Every time scientists take one more step toward it, even by the tiniest fraction of a degree, the universe answers with something new. A new state of matter, a new quantum effect, a new glimpse of how reality behaves when you take away almost everything except its barest essentials. If you were to stand in one of these labs and look at a monitor showing a cloud of atoms cooled to nearly absolute zero, you would see something that feels almost impossible. A ghostly, shimmering cloud suspended in the center of a vacuum chamber, sitting at a temperature where motion has nearly stopped, but not entirely. The atoms blur into one another, becoming less like individual particles and more like pieces of a single, quiet wave. It is not just cold. It is a kind of stillness that feels alive in its own strange way. Now, let us step even further down into this deep quiet, where one of the strangest and most counterintuitive behaviors of the universe begins to dominate: quantum tunneling. This is where particles stop caring about boundaries. It is where walls no longer mean stop, and where matter reveals a side of itself that feels less like physics and more like a magic trick written into the source code of nature. In our warm, everyday world, boundaries are simple and absolute. If you throw a tennis ball at a brick wall, it bounces back. If a roller coaster does not have enough speed to climb over a hill, it rolls back down. This is the logic of classical mechanics that we live by. But at the quantum level, things do not work that way. Down here, particles do not behave like little solid billiard balls. They act like waves, and waves can do something that solid particles should never be able to do. They can spread out, they can stretch, and sometimes they can slip through barriers as if the barriers were not there at all. This is quantum tunneling. It implies that it does not matter if a particle doesn't have enough energy to cross a barrier in the usual way. There is always a tiny, non-zero chance, calculated by the strange rules of quantum mechanics, that the particle will simply appear on the other side. Most of the time, this chance is vanishingly small. In our warm, noisy world, where particles are bouncing around chaotically, these quantum effects are usually drowned out by a storm of random thermal motion. But in the frozen stillness near absolute zero, where nearly all thermal motion has been stripped away, those tiny probabilities no longer hide. They stand out. At these temperatures, particles are no longer distracted by heat. They settle into their lowest possible energy states, and their quantum nature comes into sharp focus. Their wave-like behavior dominates. Instead of behaving like individual marbles located at a specific point, they smear out into probability clouds. And when those clouds brush up against a barrier, a piece of the cloud leaks through, not metaphorically, literally. That is tunneling. In laboratories cooled to billionths of a degree above absolute zero, scientists have watched this happen. They have trapped atoms in optical lattices, tiny grids made of intersecting laser beams, and seen them do something impossible. Instead of sitting locked in their assigned spots, some of the atoms simply vanish from one spot and reappear in another, without ever crossing the space between in any way we would recognize. It is not that the atoms are breaking the rules. It is that we have peeled back enough layers of temperature to see the rules that were there all along. And tunneling isn't just a laboratory curiosity. It is the key to much of the universe's hidden machinery. Consider the Sunday, the fusion reactions that power our star, and by extension, all life on Earth, depend on tunneling. Protons in the heart of a star are positively charged and repel each other fiercely. Under normal classical physics, they do not have enough energy to overcome this repulsion and collide to fuse. But quantum tunneling gives them a way to cheat. It allows them to slip through that barrier of repulsion just often enough to fuse and release energy. Without tunneling, the stars would never burn. Without tunneling, the universe would be cold and dead. But in the frozen world near absolute zero, tunneling takes on an even more direct role. In superconductors, for example, pairs of electrons called Cooper pairs can tunnel through barriers effortlessly, creating those currents that flow forever without losing energy. In quantum computing experiments, scientists rely on tunneling to manipulate bits of information in ways that classical physics would call impossible. At this temperature scale, tunneling isn't just an occasional oddity, it is the main event. What makes all of this so haunting is how it reshapes our sense of what is real. At ordinary temperatures, we can pretend that the world is solid and definite. Things stay where they are. Barriers hold. Time flows linearly. But in the frozen quiet, at the edge of absolute zero, the world loosens its grip on that comforting solidity. Particles move in ways you cannot point to or watch. They simply exist in more than one place at once. And sometimes, they decide to emerge where you least expect them. And the deeper you follow this descent, the more it feels like you are stepping out of the world we know and into one that was always running underneath it, hidden by the noise of heat and motion. Here, near absolute zero, that noise is gone. The whispers of the quantum world are no longer whispers. They are the only sound left. If tunneling shows us how matter behaves when the cold strips away the ordinary, then the next question leads us to something even stranger. What about life itself? What would happen if something living, something breathing, thinking, and pulsing with biological rhythm could touch this edge of frozen reality, where motion slows, energy fades, and the rules we know give way entirely? We have seen what happens to atoms. We have watched matter lose its individuality, slip into ghostly quantum states, and tunnel through barriers as if the rules of the ordinary world no longer apply. But now comes the stranger, more haunting question. What if life, our kind of life, built from warmth and motion, could ever touch this place? What if we could bring biology to the edge of absolute zero, where motion stops and the universe holds its breath? Life, as we know it, is fundamentally built on motion. Every cell in your body is a factory of kinetic energy. Every spark of thought in your brain is an ion moving across a membrane. Every chemical reaction that fuels your existence relies on molecules crashing into each other with enough speed to bond or break. Heat is not just a byproduct of being alive, it is the engine. Proteins fold, enzymes act as catalysts, and DNA unzips and replicates, all in a constant, restless dance driven by thermal energy. Even at rest, even in the deepest sleep, life is never still. It hums with motion. It depends on it. Now, imagine taking all of that complex machinery and lowering it, not just by a little, not to the uncomfortable cold of a winter night, or even the deep chill of liquid nitrogen, but down, far down, toward the silent edge near absolute zero. As the temperature falls, that essential motion slows. The biochemical reactions that make thought, memory, and heartbeat possible begin to lag. Below a certain point, they stop entirely. The machinery of life is not built for this kind of stillness, for For us, the descent to absolute zero isn't just cold, it is the end of activity itself. And yet, here is the strange part. There is a way in which this is already true. In the field of cryogenic science, researchers routinely freeze biological material close to these extremes. Not living people or whole animals, at least not yet, but individual cells, embryos, and simple tissues are preserved in liquid nitrogen. By lowering their temperature far enough, scientists slow every process inside them until nothing changes, nothing moves, nothing decays. It is not life as we usually define it, buzzing with activity, but it is not death either. It is something in between, a state of being paused, suspended in a kind of artificial stillness that can last for years, even decades. This is not absolute zero, of course. It is still warm by quantum standards, but it brushes against the same profound principle. The colder you get, the slower the clock of biology ticks. In theory, if you could keep cooling a living system further and further without ice crystals shattering its delicate cell walls, you would approach a kind of perfect stasis. No aging, no biological decay, no movement forward in time, at least not in the way we experience it now. But what happens if you push it even further? If you could bring a complex living system down to the edge of absolute zero without breaking it, would it still be alive? Or would it become something else entirely? Would it simply be frozen matter, indistinguishable from the dead atoms around it, waiting for heat to return like a dormant seed? Or would it exist in some strange quantum limbo, suspended in the same ghostly quiet, where even time itself seems to lose its urgency? There are experiments that hint at this boundary. Physicists have cooled single biological molecules, proteins, and viruses to near absolute zero conditions and seen them fall into perfect quantum coherence, behaving as one unified wave. Life, however, is not a single particle. It is a system, a vast, tangled network of interdependent processes, all of which depend on chaotic movement. And if you drain away that movement entirely, you don't simply pause life, you erase the difference between the living and the non-living. And maybe that is why this question feels so heavy. Absolute zero isn't just a number on a scale. It is the place where the dividing line between alive and inert blurs into something meaningless. It serves as a stark reminder that everything living is just organized motion, and if you strip the motion away, you are left with the same quiet matter as a rock or a star. But there is another side to this philosophical coin, one that is harder to ignore. If life could survive this kind of stillness, if somehow there were a way to reach this deep frozen edge and hold ourselves there, it would be like stepping out of time. No aging, no change, no end. In the coldest imaginable state, you wouldn't be dead, but you wouldn't be alive in any way we recognize. You would simply wait, perfectly preserved in a universe where nothing moves. And maybe that is the closest we will ever come to touching eternity. Not in fire, not in chaos, but in a silence so deep that even time forgets how to move forward. But before we can follow that thought too far, there is something else waiting in this frozen descent. Because if life as we know it cannot quite reach this place, there is one thing that can: the particles themselves. And when they get this quiet, they don't just slow down. They become something so silent, it almost feels supernatural. Now, we are moving into a place where even the faintest trace of motion fades into something almost imperceptible. We have been talking about atoms slowing down, about heat draining away, about matter transforming into ghostly quantum states. But if we descend further, we reach the quietest point imaginable, the silence of particles. This is a place where movement no longer feels like movement, where time stretches so thin it almost disappears, and the universe itself seems to hold its breath. In the world we know, nothing is ever still. Even a rock sitting motionless in your hand is buzzing with furious activity at the microscopic level. Its atoms vibrate, its electrons spin in orbit. Every particle hums with a quiet background music of temperature. But at the edge of absolute zero, that music nearly stops. Every vibration slows. Every collision fades. And what is left is a kind of order that feels alien. Matter is reduced to the simplest, most motionless version of itself. But here's the catch, the rule we keep coming back to. The silence is never perfect. No matter how much you cool a system, you cannot strip it entirely of energy. 0-point energy remains. That faint hum of quantum mechanics is always there, a reminder that even in the coldest, stillest place imaginable, the universe can never be entirely quiet. But compared to the restless, chaotic world we live in, this hum is different. It is not the noise of disorder. It is the sound of the universe at its lowest register, the bare minimum motion that reality will allow. When you look at matter in this state, you see the world stripped down to its foundation. Particles aren't bouncing wildly or colliding randomly. They are synchronized, their behavior dictated by quantum mechanics alone. It is the silence of a system that has been drained of almost everything except its most fundamental laws. And in that silence, matter begins to reveal things that we can't see anywhere else. This is where the lines between particles blur. This is where Bose-Einstein condensates form not as an exotic exception, but as the natural state of things. Millions of atoms, once separate, once noisy, collapse into one single quantum identity. The usual individuality of matter, its tendency to break apart into countless tiny pieces, is replaced by an eerie unity. It is no longer a crowd of atoms. It is a single, quiet entity. And in this state, strange things happen. Fluids that would normally resist motion lose all friction. Electrons stop scattering and begin to flow forever. Barriers that should block particles become irrelevant as tunneling dominates. It is a world where the laws of motion feel rewritten, not because they have changed, but because we have finally pushed past the layers of heat and randomness that were hiding what was always there. And then there is time, because if movement slows, if collisions fade, if entropy nearly vanishes, time begins to feel different. It is not gone, but it is stretched, thinned out to the point where the distinction between one moment and the next starts to dissolve. Down here, in the silence of particles, time doesn't rush forward like a river. It lingers, it hovers. It feels less like a flow and more like a still, deep pool. This is why the silence of particles matters. It isn't just an extreme condition or a laboratory trick. It is a way of seeing the universe without the noise of everything else layered on top. When scientists create these states in their laboratories, they are not just cooling atoms for the sake of breaking records. They are peeling the world back to its most fundamental state, the skeleton of reality, exposed by the absence of motion. And this silence isn't empty. It is full of information. It is where quantum mechanics speaks the loudest, where the smallest, strangest rules of the universe stop being background details and start defining everything. It is where we learn what matter really is, what energy really means, and what is left when you take everything else away. If this is what happens when particles fall quiet, the next question is even deeper. What is temperature really? And what does it mean to speak of cold and heat at all? If at the bottom of the scale, silence and motion blend into something that no longer feels like either one, it is time to pause and ask a question that has been quietly sitting underneath everything we have been talking about. We have spoken of cold and heat, of motion and stillness, of particles slowing until they nearly stop. But what does temperature actually mean? What is it that we are measuring when we talk about degrees, about Kelvin, about how close something is to absolute zero? And why does this idea, which seems so simple on the surface, lead us straight to the foundations of the universe itself? Temperature, at its core, isn't about numbers on a glass thermometer. It isn't even about how something feels when you touch it. Temperature is motion. Not motion in the way we see it every day, like a car rolling down a street or a planet orbiting a star, but microscopic motion. It is the invisible dance of atoms and molecules bumping into each other, vibrating, colliding, and constantly exchanging energy. When something is warm, it simply means those particles are moving quickly, crashing into one another with more force and frequency. When something is cold, their motion slows. That is it. No mystery, just motion. And yet, if you follow that motion downward, if you take it away piece by piece, you eventually reach a strange boundary, a place where the particles cannot slow down any further because there is no more motion left to remove. That is absolute zero. It is the point where temperature is no longer about speed or energy because there is nothing left to give. This is why absolute zero has always been such a profound idea. It is not just about cold. It is about the very bottom of motion itself. And when you understand that, you start to see why temperature connects to everything from the behavior of stars to the way time flows, to the strange, quiet, quantum effects that only appear in the frozen dark. But here is where it gets even more fascinating. Temperature isn't just about individual particles moving around. It is about how those particles share energy. In a hot object, energy is spread out chaotically. Molecules collide at random, constantly trading speed and direction. That chaos is what creates heat. But as you cool something down, the collisions slow, the exchanges become less frequent, and order begins to creep in. And when you get close enough to absolute zero, that order becomes overwhelming. Instead of countless particles each moving in their own way, you start to see the emergence of collective behavior, particles acting together as if they are parts of one larger thing. That is what happens in Bose-Einstein condensates, in superconductors, in superfluids. Temperature isn't just a measure of how fast anymore. It becomes a threshold for transformation, a marker of when ordinary matter gives way to something entirely different. And this isn't just an abstract concept. It changes how we see reality. When scientists cool something to 1/1000th of a degree above absolute zero, they are not just making it colder. They are creating a new environment where the usual rules collapse. In that world, temperature stops feeling like a simple scale and starts to look more like a key one that unlocks phenomena invisible at any other point on the thermometer. Even more strangely, temperature is tied directly to entropy, that measure of disorder we talked about before. As temperature drops, entropy falls with it. At absolute zero, entropy reaches its theoretical minimum because there is no motion left to create disorder. The system isn't just cold. It is almost perfectly ordered, stripped of every unnecessary detail. That is why scientists see these bizarre quantum effects down here, because all the thermal noise is gone. and the raw skeleton of reality is left behind. But there is one more layer to this. Temperature isn't only a property of matter, it is also a property of information. Physicists studying black holes, for example, have discovered that even these collapsed objects, places where matter is crushed out of existence, can be described in terms of temperature and entropy. In other words, the same idea that tells you how warm your coffee is also describes the deep physics of the universe's most extreme objects. And maybe that is the point. Temperature isn't just about cold or heat. It is a language. It is a way of describing how energy moves, how matter behaves, and how order and disorder shape the world. When we talk about absolute zero, we are not just talking about a number. We are talking about the floor beneath that language, the ultimate stillness against which all motion is measured. But if that is true, if temperature is really about motion, energy, and information, then what happens when the universe itself keeps cooling? What happens if one day everything, every star, every planet, every particle falls toward that silent floor? Next, we are going to step away from the laboratory, away from the microscopic world of atoms, and look at the universe itself, its far future, its last horizon, and ask, could everything one day sink into absolute zero? To understand this, we need to look not at where the universe is now, but at where it is heading. Right now, the universe is expanding. Space itself is stretching, carrying galaxies farther and farther apart. And as it does, the leftover heat from the Big Bang, that faint cosmic glow we call the cosmic microwave background, is cooling. Billions of years ago, that glow was scorching. Today, it is just 2.7 Kelvin, only a few degrees above absolute zero. And if this expansion keeps going, it will keep cooling over unimaginable stretches of time. The stars will burn out. The bright, blazing suns that fill our night sky will exhaust their fuel one by one. The small ones will fade into dim embers. The large ones will collapse, explode, or leave behind black holes. And once those black holes finish devouring what they can, even they will slowly evaporate through a process called Hawking radiation, shrinking away into nothing over eons. What happens then? You are left with a universe that is almost entirely dark. No stars, no galaxies bright enough to see, just a thin mist of particles scattered across space. And those particles, too, will keep cooling. Every interaction between them will become slower, every transfer of energy weaker, until almost nothing happens at all. This is what physicists call the heat death of the universe. But it is a misleading name because it isn't hot. It is the opposite. It is a future of freezing emptiness, where all usable energy has been spent and there is no more work left to do. It is a universe drifting downward toward absolute zero, not in one place, not in one experiment, but everywhere, all at once. But here is the strange part. Even then, it will never quite get there. Just as in the lab, where the third law of thermodynamics holds the line, the universe itself will obey that same rule. Absolute zero will always remain just out of reach. Particles will retain their 0-point energy, that faint hum of quantum motion that can never fully be erased. There will be no heat, no life, no movement in any familiar sense, but there will still be that last whisper of existence, a quiet vibration at the foundation of reality. And in that frozen future, time will become something almost unrecognizable, without stars, without heat, without entropy increasing in any meaningful way. Time will stop feeling like a river. It will flatten out into a kind of endless stillness where nothing changes because nothing is left to change. The universe won't end with a bang or a collapse. It will end with a kind of perfect, inescapable quiet. This vision isn't the only possible ending for the cosmos, but it is the one that follows naturally from what we know now. The same laws of thermodynamics that keep absolute zero out of reach in our laboratories also stretch their influence across the entire universe. They tell us that everything is slowly running down, losing energy, becoming simpler, colder, and quieter with each passing epoch. And in that sense, absolute zero is not just a number on a thermometer. It is the destination written into the fabric of reality itself, not because we will ever reach it, but because everything is falling toward it, one slow step at a time. Yet, even in that bleak stillness, there is something oddly comforting. The same rules that make the universe burn with stars also ensure that in the very end, it will rest. Not in fire, not in violence, but in silence. But before we settle into that far-off picture of eternity, there's one last thing we need to understand. If the universe is always sliding toward this frozen horizon, what happens to the laws of physics themselves when they are pushed that far? Could they change? Could new rules emerge, hidden in the deep cold, waiting for the end to reveal them? We have already seen how near absolute zero conditions in laboratories change the rules. Atoms stop acting like individuals. Matter collapses into quantum states. Friction vanishes, and electricity flows forever, without resistance. These are not just oddities, they are hints. They tell us that in the deep cold, the familiar version of physics is only a thin surface layer. Beneath it is something older, stranger, and far less concerned with the boundaries we use to organize the world. Now, imagine applying that not to a tiny lab experiment, but to the entire universe. As the cosmos cools, energy thins out, stars fade, galaxies grow dim, and in that unimaginable future, the universe would be dominated by the physics of the cold, rules that we only glimpse today in brief. Controlled bursts in our laboratories would become the standard. Quantum mechanics, for example, wouldn't just be a set of principles for tiny particles. It would be the language of everything. Without heat to drown it out, quantum effects would no longer be confined to the microscopic. They could stretch across distances, binding matter into coherent states on scales we can't currently imagine. It wouldn't be a world of planets and stars anymore. It would be a world of quantum fields, silent and vast, where the distinction between one thing and many things might simply stop mattering. And what about information? In this frozen cosmos, where change slows to an almost perfect stop, the information written into the fabric of the universe might no longer scatter and decay. It might settle into a final, unchanging pattern, a record of everything that ever happened, suspended in a universe that has nothing left to do but keep existing. This is why the deep cold isn't just an ending. It is also a kind of unveiling. Heat hides the true foundations of reality. Motion covers up the stillness underneath. But as the universe cools, those layers are stripped away. What is left might not look anything like the world we know, but it would be built from the same rules revealed in their purest form. And maybe that is why absolute zero, even if it is unreachable, has always been such a powerful idea. Because it isn't just the absence of heat, it is a threshold. Cross it, or even come close, and you stop seeing the universe the way we have always seen it. You start seeing it the way it is, when everything unnecessary has been stripped away. We have followed the cold from the restless motion of atoms to the quiet hum of zero-point energy. We have watched matter dissolve into ghostly states, seen time lose its urgency, and imagined a universe where even stars and galaxies have faded into silence. And now there is nowhere left to go, no further to descend. Only a kind of stillness so deep it feels less like an ending and more like the quiet that has always been waiting underneath everything. This is the stillness of nothing. Not emptiness, not absence, but the baseline of reality itself. Here, at the unreachable edge of absolute zero, there is no heat left to spill, no motion left to slow. Every atom has been pressed into its lowest possible state. Every trace of entropy has been pared down to the faintest whisper. It is not dead. It is not lifeless. It is simply quiet. If you could stand here not with your body, but with your mind, you wouldn't hear anything. You wouldn't see anything moving. Time would stretch until it barely seemed to matter at all. And in that vast, frozen silence, the universe would look different. Not because it had changed, but because all the layers of motion and chaos that normally cover it had been stripped away. For the first time, you would see what was always beneath it all. The calm, unshakable ground on which everything else is built. And strangely, there is something comforting about that. Absolute zero isn't just the bottom of the thermometer. It is a reminder that beneath all the heat and motion, beneath the noise of life and the restlessness of stars, there is a deeper order, a quiet foundation that holds even when everything else burns out. It is not a place we can ever touch, but it is there, anchoring the scale of the universe, defining the boundary between what can move and what can never quite stop. We will never reach it. The third law of thermodynamics will keep it forever out of reach. The same way the horizon always stays one step ahead when you walk toward it. But maybe that is what makes it beautiful. It means there is always something left to chase. Always another fraction of a degree to explore. Always one more hidden truth buried in the cold. And when you think about it like that, absolute zero isn't really an ending at all. It is the quiet underneath every beginning. It is the silence that has always been there, waiting behind the scenes, while everything else moves and changes and burns. And even if we never touch it, even if we only ever approach it, it gives shape to everything above it. The warmth of your own body, the fire in the stars, the heat of the first moment of the universe itself. So here we are, at the bottom of the thermometer. No motion left to slow, no heat left to lose, just the deep, steady hum of reality at its quietest, holding the universe together while it rests. And maybe, if you let yourself settle here for a moment, you can feel a piece of that quiet too. The kind that doesn't rush, the kind that doesn't demand anything, the kind that just is. Thank you for drifting here with me. If you found comfort in this stillness, if this slow walk to the edge of cold has given you a place to breathe, I'd be grateful if you left a like, maybe even subscribed, so we can keep exploring the quiet corners of the universe together. Now, just rest here for a while, in the calm, in the quiet, in the stillness of nothing, because for now, there is nowhere else we need to go. And as we leave this frozen horizon behind, you can feel the quiet lingering like a weightless blanket stretched across the mind. We have drifted down from the restless heat of motion to the soft hum beneath it all, from atoms that dance to a universe that may one day fall silent. And if there is one thing this journey toward absolute zero shows us, it is that even in the coldest, stillest place imaginable, the universe doesn't stop, it simply rests. So if you are lying there, letting this calm settle in, take a moment and let it stay with you. The stars will keep burning for now, the world will keep turning, and motion will return. But here, For just a little while, you have been as close as anyone can be to the quiet at the bottom of everything. For now, just rest, close your eyes, and let the sound of the universe's stillness stay with you. Because even in the deepest cold, there is comfort in knowing the silence was always there, waiting.